considered when objects interact. Ooh, and I have it too big. Okay, so that means when they collide, okay? So these were the collisions we talked about last time. So this falls under the law of conservation of momentum. It means your total momentum at the beginning has to equal your total momentum at the end. If you prefer to call it the total momentum before equals the total momentum at the end. And then we talked about this one a minute ago, what makes an collision elastic. In elastic collisions only, kinetic energy is conserved. So that means my total kinetic energy at the beginning has to equal my total kinetic energy at the end. Everybody is here. Okay. Oh. You good? Okay, we're going to come over to the middle then. What we filled out last time was the right-hand side, the how many objects. We're now going to do the more than one, okay? So previously we filled out this side for one object. Now we're going to go through and do the steps for more than one object. So if you have a bunch of objects, do they interact with each other? So in order to interact with each other, they need to have some sort of collision, or they're pushing off from each other. So they collide, or they explode, or they push off. Oh, I did that with cursive. Here you go. I know they don't teach cursive. Did you guys learn cursive? No, yeah, some of you. It's like they got rid of it for a while and then they realized it makes connections in your brain. Learning to write in cursive actually grows some extra things in your brain. So they've started going back to it now. There's some really interesting studies about connections between your brain and writing things by hand. That's why I make you guys write so many things by hand, trying to grow your brains. All right, so are they interacting with each other? If they do not interact with each other, all you got to do is calculate the total momentum. So that's the easy one. We calculate one total momentum, and we don't have to worry about it. And the total momentum is just the momentum of each piece added together, however many objects you have. There's no worrying about a before and after. There's no worrying about if the momentum changed.
I have a question, Ms. Gill.
Uh-huh.
You know the squiggly line. Why is it always added in
Because it actually means sum of whatever follows it. It's a summation sign.
Okay.
It's a Greek letter called sigma, I believe, but they use it in math to mean add everything up. So they use it as sum of and then whatever follows. Okay? All right, so going back over here. So now we're going to go if they do interact with each other. We need to look at is, are they combined at the beginning? Okay, so are they combined at the beginning? So If yes, then we need to know is, are they moving at the beginning? Most of the ones we're going to do, they're not going to be moving at the beginning, but you are going to see a couple of examples of them where they have an initial velocity. So if they're moving at the beginning, we have a different equation than if they're not moving. If they're not moving at the beginning, then the total momentum is equal to 0 initially. And we did this equation last time for the explosion type of collision, where we said they have to have equal momentums then, but in opposite directions in order for them to add up to 0. If they are moving, it looks like a reverse perfectly inelastic. You add their two velocities together, multiply it by the initial velocity, and then that has to equal their individual momentums afterwards. So examples of these where they're combined initially. It would be firing a gun as a good example, or the cannonball. Throwing something, so thrown objects are a good example of this type of collision. We call them all explosions. So these all fall under the explosions category. You could also have two people push off from each other. So if you each were on skateboards or rollerblades or something, and you were standing there at rest and you pushed each other, you would go backwards. Alright, so now we've dealt with, are they combined at the beginning? So now we're going to look at, what if they're not combined at the beginning? So, everybody's good? Alright, what if they are not combined at the beginning? Then we need to look at, are they combined after they collide? So, are they stuck together afterwards? So, if they're not, the equation looks like the, oops. Oh my god, let me use whiteout. I wanted to get through a whole one without whiteout. Alright, the mass 1 times its initial velocity plus mass 2 times its initial velocity has to equal the final momentum of object 1 plus the final momentum of object 2. So the mass 1 times its final velocity plus mass 2 times its final velocity. That's going to be the equation to determine their velocities before or after. It's going to depend on the information you're given. So then you have to look at, does the total kinetic energy at the beginning equal the total kinetic energy at the end? Because that's going to determine whether you have an elastic collision where the change in kinetic energy is equal to 0. There's no change in kinetic energy. So this objects here would have no damage or deformation. If the kinetic energy is not the same before and after, then you have the inelastic collision. Kinetic energy is decreased in an inelastic collision. So this means you do have some damage or deformation. So we talked about it with an accident, when the cars bounce off from each other, but they have damage to them. They got dents or crumpled up or something. You have something going on like that, okay? That's where the kinetic energy goes to. All right. So moving over, so we're going back up here. Are they combined after they collide? So if they are combined after they collided, then that means you have a perfectly inelastic collision. Perfectly inelastic collision, and that means that the individual momentums before, we still add those together. But then afterwards, they're going to have one large mass times some final velocity there. All right, we need to fill in one final piece over here in between these. I forgot to have you write that, okay? You must calculate the kinetic energy. The initial total kinetic energy and the final total kinetic energy to determine whether it's elastic or inelastic. The only way to tell. It's the only difference between those, and it's the only way to tell if they are, if it's elastic or inelastic. All of that fun stuff. I made sure on the review that you will get on Monday that I designated challenge problems. So for this test, if you want an A, you are going to need to look at, you're going to need to be able to do the challenge problems, okay?
Are we going to be able to use this one, guys?
You can use whatever you want on the test. They're still all open notes. Okay. All right. So momentum practice number 4. On the front, I want you to, on number 4, when it says calculate the impulse, I want you to do it from the time equal to 4 seconds to the time equal to 8 seconds. The whole thing requires you to do area under the graph, and you don't need to do that. Okay, that means this one has an answer on the back. It means that we need to update our answer on the back. So if you flip over and find 4C at the bottom, we aren't doing what they have here with the first triangle and all of that. So it should be a negative 32. Sorry, for some reason I was doubting the math in my head. All right, since we're on the back, this is optional. You don't need to do this. It's review from first semester, so you can go ahead and cross off question, whatever this physics basics question on the back is. Number 5 is going to be an optional challenge problem. So it won't be covered on the quiz per se, but there might be some conceptual questions on it on the test. You need to use conservation of energy for parts of it. This part C needs a conservation of energy, and part A needs a conservation of energy. Okay? So if you're going to do that one, you got to use some conservation of energy. The only momentum piece is part B. I'll put it on the answer key so you can see it if you want to try it, but you don't have to. All right, on the back of this page, we already talked about those, so go to the second page, okay? Just a reminder, this is your height. So you do need to use some conservation of energy down here for part C and D. So C and D can be optional. We'll do a couple together on Monday. I do think I put 1 or 2 on the review for you. Like I said, if you want an A on the test, you're going to have to understand conceptually what's going on. These are okay. Number 3 is also going to need some conservation of energy, and this is an optional question as well. So this one's an optional challenge problem. So again, these will not be on the quiz per se, where you're using conservation of energy to solve for them, okay? So that's an optional. And then there are some optional ones on the back of this page. Starting with number 5. So number 5 through number 8, if you want to challenge yourself, see what you remember, but they're optional. So they will not be on the quiz next time.